I will try to keep the schedule, and I must start thanking Anil Misra for two reasons. We wrote together a paper on which this presentation is based, and second, he was criticizing me friendly but sharply for improving the presentation. So I start giving three examples of metamaterials, but you have seen already very interesting examples, and I was relieved in discovering that the scheme, the general scheme I will try to present you, includes what has been presented by before, and this means that the generality which I try to attain is for the moment safe. So everybody knows that there is a negative Poisson effect. We know that with this microstructure you can get, on the right, you can get negative Poisson effect. I want to underline that the existence of auxetic material did not contradict any basic physics principles, whatever was believed before Lamé and Green, and this result is simply related to a theoretical reasoning which was developed by Lamé and Green about the class of objective isotropic elastic energies in first gradient continua. This theoretical debate produced this specimen of artery used in reconstructing, saving people with atherosclerosis. Also, I want to remind you that Milton and Cherkayev invented a pentamode material. This structure is described there. It is a very well-known example, which has the very peculiar property of being a fluid in small deformation regimes. So what happens is that in order to see that it is a solid, you need large deformations. So why metamaterials? How getting them? There is a demand of materials with improved exotic macro scale properties. Architectured materials are aimed at filling the gap between performances required and available materials. You know, I'm a little bit Francophile. In France, they like very much architectured materials, so I like this also. What it means is, we mean with this term, we refer to any material having specific properties at macro scale obtained via relevant, predefined morphological and or topological design at micro scale. In principle, it should work whichever is the basic material which you have used for building the architecture. Of course, we know that additive manufacturing is giving us the possibility to transform these dreams into reality. Here are some micro and meso architectures. Why I want to underline, wanted to show them to you, and you have seen, I repeat already, some very interesting. In every case, you have a meso level, a meso length scale, where you can describe the system, model the system using springs, rigid bodies, masses. This is the revenge of Lagrange. And I'm very pleased to discover that even in the United States now, they are using Lagrange equations, albeit they were forbidden for a long while there. Okay, the problem of synthesis is not new. The mathematical methods to be used must be similar to those already used for designing analog circuits. Here, there are few old people. I have studied at the beginning of my career how to build the analog circuits for field equations of Maxwell, compressible fluid flow. Analog computers were used for calculating solutions using electromagnetic phenomena. And there was Gabriel Krohn was supported by General Electric, and he was considered the big man in this field. So you discretize partial differential equations and you find the analog finite dimensional Lagrange model, and then you look for the circuit governed by this Lagrangian model. It is interesting, there is a nice mini symposium here which has been organized by Boris Lesoir. I want to remind that there are multiphysics metamaterials, which you can call piezoelectromechanical metamaterials, in which the microarchitecture involves some piezoelectric actuators and an electric circuit. The basic concept in this metamaterial consists in the transformation of mechanical energy in an optimal way into electric energy and vice versa by using analog circuits. Now I'm becoming old. I proved maybe 20 years ago that in order to have the maximum of energy transfer in linearized system, you need that the electric circuit interconnecting the piezoelectric actuators must be the analog of the mechanical system to which it is attached. And the result is that you have a piezoelectromechanical extensional beats, and you have here you can damp the vibrations of a beam with a unique electric circuit. What is interesting is that you can get multimodal dissipation with a unique dissipative circuit. And these numerical simulations prove that on the right side you have the ISO voltage line in the homogenized system. You have the first mode which is damped, the second mode which is damped in the optimal time, because in the theory of control you have optimal time damping, and if you have a number strike you can quickly get the damping independently of the applied forces, and what is interesting is that the circuit remains always the same. So the fundamental theorem in the synthesis of analog computers is based on a definition. We call elementary circuital elements the resistances, the inductances, the capacitances, and the transformers. Why? Because for every quadratic Lagrangian and quadratic Hamilton-Rayleigh dissipation function, it is possible to find a graph, and for every branch of the graph, an elementary linear circuital element, such that the obtained circuit is governed by the corresponding Lagrangian equations. Okay, so which is the idea? We must find a minimal set of elementary substructures that allows for a suitable via suitable interconnections, allows for the synthesis of every internal virtual world functional describing the deformation of continua. I don't have this general result yet, but I can show you some results which promise that this program can be pursued. So the fundamental problem in the theory of metamaterials consists in the synthesis of materials having some specific physical properties. What it means that a material has specific physical properties? Mathematical formalism will help us to find a precise meaning. Why I'm talking about the Kuhn paradigm cycle? I know I should say paradigm, but it is stronger than me. I cannot say a Greek word. I cannot pronounce a Greek word in that American way. Okay. The change of paradigm is described here. You have normal science, classical continuum theory. Then you have a model drift. Some phenomena cannot be described. Think about the famous Dejean capillarity fluid. Then you have a model crisis, ad hoc fixes. Then we change viewpoint. Instead of looking for the equation describing a specific already existing materials, okay? So instead of choosing a physical system and looking for the equations which allow for the prediction of its behavior, what we do? We choose the equations. And these equations specify the desired behavior, and then we look for the microstructure that, once homogenized, is successfully described at the macro level by the chosen equations. We need this change of viewpoint. Now, an important warning. One must be able to distinguish between physical objects and mathematical models. Okay? So, we must be able to avoid to believe that an equation is a material, which happens very often. People believe that Cauchy first gradient continua do exist and nothing else is existing outside them. This is a typical error, philosophical error, which you meet in history of science systematically. So we must avoid a dangerous ontological viewpoint. Now, let us do quickly. This drawing is taken from The Forgotten Revolution, a book by Lucio Russo, which I strongly advise everybody to read. It is very clear. So you have the world of scientific theory. Then you have the concrete reality. Okay? We are not Platonistic. Scientific theories are invented by us. They are not existing without our brain. Okay? So what happens is that you invent a theory at the top. Some concepts correspond to some aspects of concrete reality, deformation, displacement. Some concepts, look, there are some dots at the top, do not correspond to anything downstairs. Forces. Okay? Very important theoretical concepts without any correspondence to reality. Okay? But what is scientifically designed technology? What you invent using a theory which allows you to find phenomena never found before. This is not dell'Isola's theory. Epicurus did this. So I'm fighting a battle which has been won several times in history of science. Okay? Just to go ahead, on the right you see a book. You know, this book was a book written by Archimedes, Difficult Mathematics. A monk erased the written ink by Archimedes, and they wrote horizontally some prayers. Okay, with a long story, I have no time to tell you. We could discover what is written in this text, and I read you some words. Archimedes to Eratosthenes, greetings. I sent a letter to Professor Paul Germain, Monsieur le Secrétaire Perpétuel. So nothing is changed. Seeing moreover in you a man of considerable eminence in philosophy, I thought fit to explain a certain method by which it will be possible for you to get a start to enable you to investigate some of the problems in mathematics by means of mechanics. French Baroquism in Greek. Okay? This procedure is no less useful even for the proof of the theorems themselves. For certain things first became clear to me by a mechanical method, although they had to be demonstrated by geometry afterwards, because their investigation by the said method did not furnish an actual demonstration. But it is of course easier when you have previously acquired by the mechanical method some knowledge of the question to supply the proof that it is to find it without any previous knowledge. I deem it necessary to expound the mechanical method because I am persuaded that it will be of no little service to mathematics, for I believe that some, either of my contemporaries or of my successors, and we are his successors, will be, by means of the method, when once established, be able to discover other theorems in addition which have not yet occurred to me. You know, this man is talking to us. First, then, I will set out the very first theorem which became known to me by means of mechanics, namely that any segment of a section of a right-angled cone, a parabola, is 4/3 of the triangle which has the same base and equal height. He calculates integrals. Then I will give the geometrical proof of the proposition. So he knows that mathematics is something and physical reality is something else. Okay? 3rd century before Christ. Okay? Well, now I switch to this other presentation, which partially I presented in Paris. Mechanics is the first mathematized theory in history of science. Mechanica Problemata is an apocryphal text attributed to Aristotle. In it, the principle of virtual world is already applied systematically to predict the functioning of machines. The mathematical formalism on which it is based is the Euclidean geometry. This is a unifying theory. Okay? It gives. Okay, now, I am a senile old, but why are we so interested in understanding how mechanics was at first formulated? To get hints about invention methods of novel theories. We don't have a theory for building theories. So we must be like the student in the workshop of Michelangelo. He goes learn and he learns how Michelangelo is drawing. We must go to Archidas and say, how did you invent the equilibrium of the lever? I want to invent new metamaterials. By the way, do you believe that Archidas had no problems? Plato reproached Archidas for having contaminated geometry with mechanics. So it is an old story. Okay? By the way, Diogenes Laertius claims that Archidas is the founder of mathematical mechanics. Okay? Now, Lagrange formulation of the principle of virtual velocities. I believe, and I'm working with Yves about that, we believe that Lagrange did reconstruct the ancient formulation of the principle of virtual world, which has been lost. Mechanica Problemata is a set of exercises. Okay. If a system is in equilibrium and if a small movement is imparted to this system, then the sum of the powers multiplied by the distance will be equal to 0. The other words, why are they there? Lagrange has no inner product. So he has to write that way. Okay, but we can write this with functional analysis and the theory of distribution. By the way, Lagrange uses the word power instead of force. This is because he wanted to follow Galileo notation. Okay, but we agree that Lagrange formulation is so general that every version of the principle of virtual world formulated up to now is included, and it uses the minimum possible mathematical concepts. Which is the most basic concept in mechanics? Forces or work? Truesdellians claims that mechanics is to be founded on the concept of force. Truesdell claims that balance laws can be induced from experiments. Instead, D'Alembert and Lagrange were persuaded that the most fundamental concept in mechanics is work. Okay, Einstein maybe said, there is never enough experimental evidence that can prove that I'm right, while a single experiment can prove that I'm wrong. So Archimedes understood this. Okay? Here you find the basic idea of Popper falsificationism. In French, you use another, not falsificationism, but you have changed the name just for causing troubles. Is it worth to ponder about this epistemological and historical debate nowadays? By the way, is mechanics something for old people, or we can teach to young people how to make science in mechanics? The answer is yes. In fact, if one must refrain from the inductivistic belief that laws of physics can be induced from experimental evidence. Here is the story, go to read it, by Bertrand Russell, who talks about a chicken who was an inductivist. Okay? D'Alembert believes that the principle of virtual work must be postulated a priori, and its logical consequences are the predictions to be experimentally checked. Force is a derived concept, useful, but it has no direct experimental counterpart. Okay, so the unifying idea in mechanics, but Feynman believes in every physical science, is the principle of virtual velocities, whose modern name is the principle of virtual work. I did not resist, I'm running with time, but here, D'Alembert, the forces inherent to bodies in motions, obscure and metaphysical entities which are only capable to spread shadows on a science that it is clear by itself. I must warn that in order to avoid circumlocutions, I have often made use of the obscure term of force, but I never pretend to attach to this term any other idea except those which result from the principles. Okay, and this is the way in which we must use these things. Okay, now we want to use the principle of virtual work for designing novel metamaterials or architectured materials. And how we do it? The problem must be solved in 3 steps. First, one must choose continuum theories describing the desired behavior at macro level. How we do it? We choose microscopic descriptors and we formulate the principle of virtual work. Don't try to ask me why. This is the conjecture, the basic idea of any theoretical development. We will see if it works, giving good predictions. Second, we conjecture in a specific class of microstructures having a multi-scale structure, the subclass which is candidate to be governed by the chosen macro model. This is similar to the conjecture that inductors, capacitors, transformers, and resistances are enough for the synthesis of every linear dissipative circuit. And then we make the identification of micro and macro theories via me identifying micro virtual work with macro virtual work. I must give an example. I want to show the synthesis of Timoshenko beam model. This was a paper which I wrote with Pierre Serpecher and Emilio Barchiesi. Springs, bars, you see it is self-explanatory, this drawing. The microparameters are the position of the barycenter of the bar, the angle theta I, the angles phi, which give you the change of angle of the rotational springs. Then you reconstruct the position of everything in terms of theta I, pi, and phi i's with this simple geometry, nothing difficult. Then you solve the beam theory for the flexible beam which is at the top. The vertical beams are rigid, the horizontal beams are elastic. And what you get? The potential energy of the mesoscale structure, which reads in terms of formula 3.9, where you have applied only forces at the beginning of the beam and at the end of the beam for simplicity. So you have dead loads applied, okay? Then you solve the linear elastica problem. You find the imposed boundary conditions in terms of the non-kinematical mesoparameters, and you get the deformation energy at the meso level. Remark, you have pi minus pi plus 1. You strongly want to homogenize this, forgetting a continuum model where the derivative of pi appears. Of course, you have also the energy of rotational springs. The idea of Gabbro-Piola, okay, this is the kinetic energy. We started assuming there is no mass of the flexible beams. This means that they are negligible, okay? Then, following meso-macro-Piola identification, we postulate there is a field chi, a field theta, a field phi, and chi of xi is equal pi, theta of xi is theta I, and phi of xi is phi I. So you make a macro-micro identification. Knowing the macro field, you get information about the micro field. Okay? Taylor expansion, very important. Rescaling of the elastic and kinetic energy parameters, you get this energy which you have write down. Condensation, everything which does not depend on derivatives, you can minimize with a standard minimization argument. So phi, all the phis are given in terms of w prime minus theta, and you get Timoshenko beam. It is rather astonishing. By the way, Pierre Seppecher has proven gamma convergence of that. So the heuristic Archimedes. I've shown you the heuristic method. Then with Seppecher we have proven rigorously the result. Okay. So the micro-macro identification becomes instead very difficult if one uses models based on balance of forces and balance of moments of forces. Energy is a scalar. Micro equal macro. So the debate, the epistemological debate, which I wanted to impose you at the beginning, is not useless. It is very important because it is directing us. Okay? Ehringen decided to generalize, to introduce generalized continua, but following the paradigm of Trussell. So he postulated ad hoc balance laws, one for every new kinematical descriptor at macro level. Okay? But where is the difficulty? It is very difficult without the a priori knowledge usually given by variational principles to understand which micro balance laws contribute to a certain macro balance law. I have spent 2 years of my life studying interfaces between liquid drops and vapor simply because my PhD supervisor was Trusdellian and still is Trusdellian. Okay? So the homogenization as conceived by Gabbro-Piola has these 4 steps, but I think it is better that I skip, but I gave you an example. Okay? And then, thanks God, Laurent Schwartz invented the theory of distributions. So, if you postulate that the powers expended by the actions exerted on or exerted in a sub-body B of a certain deformable body are distributions concentrated on B, then you can use the beautiful theorems proven by Schwarz. Every distribution having compact support can be represented as the sum of a finite number of derivatives of measures, all having their supported included in kappa. Therefore, and another theorem, if you have a surface, the distribution concentrated on a surface depends only on the normal derivatives of the test functions. Okay? And this will be very helpful. So, we want to invent the theory continuum mechanics. We have the theorem of Laurent-Schwarz. 8 gives you the most general internal power. Now, remark that Cauchy is using only the first gradient of velocity. The zero gradient goes away for objectivity. Okay, Green and Rivlin called the lambda times contravariant tensors lambda order multipolar stress. So this is an object which has been studied even in Anglo-Saxon countries. By the way, Hamilton was a follower of Lagrange. It is not being French, Italian, or Anglo-Saxon. It's being open-minded or close-minded, I think. Okay, so given the internal work functional, performing subsequent integration by parts on the domain boundary faces, on boundary edges, and on boundary wedges, and using the principle of virtual work, that is internal power equal external power, you get the class of admissible external interactions possible for a given continuum. Together with standard forces, dual of velocity in power, per unit volume and per unit surface, you have forces per unit line, then you have L forces, dual of the normal gradient of virtual velocities on the faces, J forces on edges, and J forces on wedges. But the integration by parts lower the order of forces which you can apply in lower dimension boundaries. Okay, this is the mathematical proof that the well-posed boundary conditions in nth gradient, the natural boundary conditions, are given by J forces, or essential boundary conditions are displacements and normal derivatives of displacements. We have not deduced them experimentally. By the way, this is not new. Nobody tries to apply shear forces to the boundary of a perfect fluid, right? So what you can apply to a continuum depends on your model. Don't confuse the model with the physical object. Don't try to say me I can apply a shear force to a fluid. You need another theory, Stokes-Navier, capillarity fluids, for describing this phenomenon. Okay. Now, I have not a fixation with a pantograph because I have written many papers on it and I do not have anything to do. The pantograph is like a capacitor. It is an essential element for synthesizing more general metamaterials. Okay, what is doing this pantograph? It is elongating without deformation energy. So there is another tragedy in Italy. Mechanics applied to machine is taught by some group of professors. Structural mechanics is taught by another group of professors. So I am an heretic. I am invading the field of another group because this is clearly a machine. You homogenize it and you get a structure. Okay? So the idea is to have micro mechanisms activated at micro level, giving at macro level second gradient materials. Now, a purist told me that bending beams are too complicated. On the left, you see a truss version of the pantographic, just to show you that I know engineering. A king post structure does the job, okay? So the idea we had in 2003 with pièce Pécher, life is flowing away quickly. We had the energy you see there, and we said, how can we synthesize this? Remark second derivative of u1 with respect to x1 squared. Okay. The crucial idea is that Piola points are the blue points. U1 and U2 are describing what is happening to blue points. Okay? Red points are those points whose position you get minimizing in condensation process. Okay? So, what happens is that you have floppy modes. Non-rigid displacement fields corresponding to zero deformation energy. Okay, then we developed and we got this result with Emilio Barchiesi. We got the energy in large deformation regimes. Okay, and the idea was using Henke discrete springs equivalent to Euler beams. Okay, so the class of microstructures, mesostructures, which we believe is suitable for doing the job is springs, rigid bars, at least for planar systems. Then I quickly tell you that we invented already third gradient beams. Beams whose deformation energy depends only on the third gradient of transversal displacement. What you do? You build Warren bridge structure. At the top you place the pantographic structure, and symbol calculations show you that it is governed by a third gradient energy. Therefore, you need not only double forces, but also triple forces as natural boundary conditions. But I show you this with pantographs. In order to block the floppy mode, you need to add a second pivot to the second blue dot there, and you block in this way normal derivatives and rotation constraints at the boundary of this one-dimensional continuum. By the way, with Antonio Carcaterra, Raffaele Esposito, and Mario Pulvirenti, we have proven a rigorous convergence of this system even in dynamic situations. Double forces are the reactive interactions, which is not a couple, and expense work on elongation. So you understand that the micro-macro identification process gives you also an effective way to interpret physically the integration by parts result which I gave you, and it was purely formal. Okay, now I start running. We wanted to synthesize a plate having deformation energy depending on higher derivatives in the plane. And we wrote this energy. You have bending of some material lines, straight lines, whose director in the reference configuration is dA. You have the elongation of these bars, and you have a shear energy related to the relative rotation of these. This energy is incomplete. Remark that not every derivative appears, second order derivative appears. You have one possible floppy mode, and you have second gradient contribution related to the beams you have there, and the bending of micro beams give you the result. Okay. Then you try the bipantographic planar sheet. Every beam is a pantographic beam. And what you have is that all these are floppy modes with zero energy. Okay? We did the macro identification, and we got the energy which we said before. With Victor Eremiev, a very good friend of mine, we have proven, actually he did prove nearly everything, that the Nikolsky anisotropic Sobolev space needed to be introduced as energy space in order to prove well-posedness results for bipantographic plates. And we found also the correct boundary conditions. Continuum models are valid even for wide-knit microstructures. Why? I don't know. I tell you that the applications is very wider than we expected. Do you remember Semvenan anticlastic deformation in the classical theory of beams? Okay. We printed in the lab of Ferdinando Riccio in Pavia this specimen, and we tested it in the lab of François Hilde in Paris. This is an experimental object, and this has been obtained via tomographic measurements, and look, very exotic behavior, no anticlastic deformation, okay? But you have also the very nice, okay, you can explore, you can go inside. Dark is more dense material, clearer is less dense material. Okay, you can see everything. I cannot speed up that, but you see the pivots which are deformed. I mean, it is the dream of mechanicians, this device. But what you get? Upper blade deforms and lower face remains not deformed nearly. And finally, you have the possibility of investigating what happens. Static arching effects are the reason of the behavior, exotic behavior of this pantographic block. And if it goes away, you will see now what happens. We can have Cauchy cuts. You can remove a part of the specimen, and you have the remaining part of the specimen, and you can check what happens at the surface. So you can measure the deformation, not contact forces. You can measure the deformation in the cut surface. Look, this is now the Cauchy cut, which you can get for studying what happens in the interior of your continuum. Okay, I must go quickly. So pantographic beams studied in Berlin, pantographic beams which behave at the beginning as a beam and then as a cable, and this is a nice phase transition elongation deformation guided. Printing bipantographic sheets has been possible, and some very exotic behavior has been observed. I need to use 2 minutes more, maybe. We have implemented normal derivatives constraints in bipantographic structures. Then, using the multiphoton lithography, we printed micrometer pantographic modules, and in the lab of Anil Misra, we have checked that millimetric pantographic modules have the same behavior as micrometric pantographic modules, which means that the idea can be used for building materials having a very small microstructure. Not only you can choose the pivot dimension in order to optimize the exerted force of the macro system. This to show you that we are doing experiments. This is for nice pictures of the This can be of interest if there is somebody here who can help me in printing these things. The space between the internal part of the pivot and the external part of the pivot for having perfect pivots in your microstructure is very important, but I must tell you that in France you have big experimentalists who know theory. Francois Hild told me that I need your theory for doing my measurements. So the experiment of luminifer ether killed Michelson and Morellet killed luminifer ether. So Francois tried to kill second gradient theories. How? He asked us to calculate the deformation of pantographic specimens. Then he used digital image correlation advanced techniques. He's already very good, but he could not follow large deformations. So he directed his code to find a part of the specimen where the theory was predicting it had to be. And look, using second gradient first row or first gradient microtheory second row, you need a lot of more calculations. We predict where each subbody should be placed, and then we look for the subbody in the image obtained experimentally, taking into account its predicted shape of change of shape, and the theory suggests where to find what we are looking for. And the final result is that we find that the theory is not falsified, okay? And the result is independent of the theory. So, I am concluding. Different scales, different models. 5 millimeters for your pantograph, second gradient theory. 1 millimeter beam theory. 100 microns, Cauchy isotropic continuum. 10 micrometers, Cauchy non-isotropic continuum models. Quantum mechanics if you go lower, okay? And I want to show you this. Oh, what happened? Oh, Madonna. He's spoiling my final effect. Au musée d'Orsay, la nature se dévoilant à la science. This is very beautiful. How can we persuade nature à se dévoiler à nous? Use variational principles. Okay, thanks a lot.